Ever pondered how a device as hefty as a refrigerator, like a helicopter, defies gravity and shoots into the sky? It's a marvel of modern engineering that leaves many of us in the same state of wonder as watching a magician pull a rabbit out of a hat. The science behind a helicopter's flight is as intricate as the gears inside a Swiss watch. It involves complex principles of physics and cutting-edge technology that's as advanced as the latest smartphone. The helicopter is not just a simple machine. It's a symphony, just like an orchestra, with each instrument or part working in perfect harmony. There's the engine, the master of lift, like the strings in a puppet show, the direction changer, acting as a compass, and the pilot's tools, each component playing a crucial role like a cog in a clock in the seamless operation of the whole. As we delve deeper into the mechanics of a helicopter, like a detective solving a puzzle, we'll uncover the mystery of how these fascinating machines conquer the skies. So hold on to your seats, like a roller coaster ride, as we're about to embark on an exciting journey into the world of helicopter mechanics. Understanding the science behind helicopters can be as thrilling as the first drop on a roller coaster or a helicopter ride itself. At the heart of every helicopter lies its engine, the powerhouse. A marvel of engineering that converts fuel into mechanical power, the engine is the beating heart of the machine, dictating its capabilities and performance. In a helicopter, the engine is tasked with a unique role. Unlike a car, where the engine directly propels the vehicle forward, a helicopter's engine is primarily responsible for powering the rotors. These rotors, in turn, generate the lift that allows the helicopter to rise into the air and move forward. So, how does this work? Well, the engine, usually powered by jet fuel or aviation gasoline, generates a high-speed flow of exhaust gases. This gas flow is directed against turbine blades, causing them to spin at high speeds. This spinning motion is then transferred through a series of gears to the main rotor shaft, causing the rotor blades to spin. The engine also powers the tail rotor, a smaller set of blades that counteracts the torque generated by the main rotor. Without this, the helicopter's body would spin in the opposite direction to the main rotor, making controlled flight impossible. The engine's power isn't just for spinning the rotors, though. Some of it is also used to drive ancillary components such as hydraulic pumps and electrical generators. These supply power to systems that control the rotor blade's pitch and provide electricity for the helicopter's various instruments and systems. In many ways, the helicopter's engine is like the conductor of an orchestra. It sets the pace and controls the rhythm, directing the various parts of the helicopter to work in harmony. Without it, the helicopter would be nothing more than a collection of metal and plastic, incapable of the incredible feats of flight it regularly performs. So, while the rotors may be the most visible part of a helicopter, it's the engine that truly drives the machine. It's the power source that breathes life into the helicopter, transforming it from a static object into a dynamic machine capable of defying gravity. In essence, the engine is the driving force that sets the helicopter in motion. The characteristic feature of a helicopter is its rotor system, the spinning blades you see on top. These rotors, not just spinning decorations, are the heart of helicopter flight. They're the equivalent of wings on an airplane. But unlike an airplane which moves forward by thrust, a helicopter moves upward by lift. Now let's delve into the science behind this. The rotor system comprises two parts, the main rotor and the tail rotor. The main rotor, the large disc above the helicopter, is responsible for providing lift. The blades of the main rotor tilt or pitch at an angle, and as they spin at high speeds, they slice through the air. This action triggers the principle of Bernoulli's theorem, where the faster air moves, the less pressure it exerts. So, the pressure below the spinning blades is greater than above, creating lift. The tail rotor, on the other hand, prevents the helicopter body from spinning in the opposite direction to the main rotor due to Newton's third law of motion. For every action, there's an equal and opposite reaction. The tail rotor provides a sideways thrust to balance this reactionary torque. Now, onto rotor pitch. Picture a ceiling fan. If the blades were flat, they wouldn't move much air, would they? The same applies to a helicopter rotor. The angle at which the rotor blades slice through the air is critical. This angle is known as the pitch. If the pitch is too shallow, the blades won't generate enough lift. If it's too steep, they could stall. So the pitch needs to be just right for optimal lift. So there you have it. The rotors with their spinning blades and carefully calibrated pitch do the heavy lifting, literally. They push against the air and the air pushes back, allowing the helicopter to climb into the sky. The rotors, in their unique design and function, are the true masters of lift. The tail rotor may seem small, but it has a crucial role to play. It's like the understated superhero of the helicopter world. It's not the star of the show like the main rotor, but without it, we'd be going in circles. Literally. The tail rotor is all about control. It helps the helicopter change direction, making it a versatile machine that can navigate in ways other aircraft can't. But how does this little rotor achieve such a big task? Well, it's all about countering the torque. When the main rotor spins, it doesn't just lift the helicopter into the air. According to Newton's third law of motion, for every action, there's an equal and opposite reaction. This means that as the main rotor spins in one direction, the body of the helicopter wants to spin in the opposite direction. This is what we call torque. So, imagine you're in a spinning office chair with your legs off the ground. If you spin a bicycle wheel in your hands, your chair will start to rotate in the opposite direction. That's torque in action. Now, if you're a helicopter, this isn't exactly ideal. You're trying to go somewhere, not just spin around on the spot. Enter the tail rotor. This smaller rotor on the tail of the helicopter counters that torque. It pushes the tail in the opposite direction to the body's spin, essentially fighting the torque. By varying the power to the tail rotor, the pilot can control the amount of counter torque applied. This means they can turn the helicopter on its axis, without moving forward or backward. So the tail rotor is like the rudder of a ship. It doesn't propel the vessel, but it steers it. It's the small but mighty component that allows a helicopter to hover in place, sidestep, reverse, and make precise movements that are simply impossible for other aircrafts. The tail rotor, therefore, is the direction changer, allowing the helicopter to move in the desired path. It's the unsung hero of helicopter mechanics, turning the impossible into the possible and the uncontrollable into the controllable. The pilot's tools, or the controls, are like the steering wheel of a helicopter. Let's dive right into the cockpit and examine these crucial components. In essence, the controls are the pilot's dialogue with the helicopter, allowing them to command its movements. The three primary controls are the cyclic control, the collective control, and the foot pedals. Each of these plays a unique role in the helicopter's operation. The cyclic control, located between the pilot's legs, is akin to a joystick. By moving the cyclic control, the pilot can alter the pitch of the rotor blades. Pushing the cyclic forward will tilt the rotor disc forward, resulting in the helicopter moving forward, while pulling it backward will make the helicopter move backward. Similarly, moving the cyclic to the right or left will cause the helicopter to move in those respective directions. This control gives the pilot the ability to navigate the helicopter in any direction. The collective control, found on the left side of the pilot's seat, is responsible for the helicopter's vertical movement. When the pilot pulls up the collective, it increases the pitch of all the rotor blades equally. This generates more lift, allowing the helicopter to ascend. Lowering the collective decreases the lift, causing the helicopter to descend. The foot pedals, located at the pilot's feet, control the tail rotor, which counteracts the torque produced by the main rotor. By adjusting the foot pedals, the pilot can control the helicopter's yaw or its rotation about its vertical axis. This allows the helicopter to turn left or right without moving from its spot, a feature that is unique to helicopters. In sum, these controls form an intricate network of commands that the pilot uses to maneuver the helicopter. Each control has a specific purpose, and together, they give the pilot the ability to navigate the helicopter in almost any direction. This level of control is what makes helicopters such a versatile mode of transportation. The controls, thus, are the pilot's tools, enabling them to command the helicopter's movements. So, how does all this science and mechanics translate into a helicopter's flight? Let's simplify it. The heart of the helicopter, the engine, powers the main rotor blades on top. These blades act like individual wings, generating lift by changing the air pressure above and below them. The faster the blades spin, the more lift they create, and up the helicopter goes. The tail rotor, the little propeller at the back, plays an essential role too. It counters the torque created by the main rotor, keeping the helicopter from spinning in circles. Next, the pilot's controls. The collective control changes the pitch of the main rotor blades simultaneously, affecting the lift. The cyclic control tilts the rotor disc, moving the helicopter in a desired direction. The foot pedals adjust the tail rotor's pitch to control the helicopter's rotation. Together, these components harmonize, creating a delicate balance between power, lift, and control. And that's the fascinating science behind how a helicopter works, a symphony of mechanics and physics.